We are now recording. Go.
Okay, hi everyone. My name is Savannah, and Mateo, Emma, and I will be presenting the data we collected and sharing what we learned from our mentor, Ken. Next slide. Today we will be talking about three things that we observed and collected data on. Mateo will be talking about the star cluster M52. I will be talking about the exoplanet transit Cutter 1b, and Emma will be talking about the globular cluster M92. Next slide.
Okay, so this is a little overview of the equipment that we used. So as Savannah mentioned a little bit earlier, or Joe mentioned a little bit earlier, everything we did was virtual. So how this worked is that we basically everyone was at home, and Ken, our mentor, has his own observatory. And with that, a bunch of programs and software and hardware that can track stars and take really good pictures of the night sky. And so this is just a little bit of overview of the software and hardware. And so for the software, you can see Maxim DL was for calibrating images. We have PhD2 guiding software. AIP for WIN helped a lot in finding the distance modulus, which I will talk about later. We used a lot of data sorting. So for that, we used Excel. And then some of the hardware that we used was Ken's 12-inch telescope, then his QSI camera, and a bunch of filters that I will talk about a little bit later. All right, next slide. So I will be talking about what we did with M52 and sort of talking about the procedure that we did to take some data on it. So next slide, please.
Okay, so first there's just some terms that you're going to need to know. One of them is a color magnitude diagram. It's a variant of the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is a graph of temperatures and magnitudes of specific stars. We use the color magnitude diagram to plot our specific star clusters, though. Sorry, next slide.
And a little bit more background. So M52 is an open cluster. And what is an open cluster? So an open cluster is a relatively small cluster of stars, which can be up to about 1,000 stars. And they are very young. And so that means maybe tens to hundreds of millions of years old. And globular clusters are larger and a lot older, which Emma will be talking about later. And they are all formed from the same molecular cloud. So these stars were all born in the same sort of gas cloud, essentially. Next slide, please. Okay, so what we did is that we were trying to find the distance from us or Earth to the M52 star field. And so how we did that is that we took 200-second exposures in two different light filters. And we took many pictures. So this, I think, was a multiple hour process. And so what we did with those is that we took those images and we stacked them to remove unwanted noise or signal. And then what we did after that is we plugged those images into AIP for WIN, and that helped us collect magnitude data. Next slide, please. All right, so once we got our magnitude data from AIP for WIN, we adjusted the B and V values to comparison stars. And these comparison stars are stars that we already knew the magnitudes of. And so we adjusted for error with these, essentially. And then from the data that we got, we just adjusted those values. And then we got a little bit more of an accurate reading. And then so what we did, as Savannah talked about a little bit earlier, we plotted the color magnitude diagram of the M52 cluster. And so from this, we were able to fit the main sequence, which is that red line there. And from that, we could determine the distance modulus. Next slide, please. And so here are the results. So what we did from here is that we applied the distance modulus to that little equation right there. And from that, we were able to calculate that the distance from Earth to M52 was about 1.58 kiloparsecs or 5.17 kilolight years. And from actual databases and professional astronomers, the actual distance is about 1.4 kiloparsecs and 5 kilolight years. And so for an amateur high school observatory, I think that was pretty good reading. Next slide.
Okay, and now for Cutter 1B. Next slide. For some background information, an exoplanet transit is when a planet goes in front of a star. The brightness of the star decreases as the planet passes in front of it, and using some devices and calculations, we can learn a lot from that planet. Next slide. Our goals were to find the radius and size of the planet Cutter 1b. To accomplish our goal, we had to first calculate how long it took Cutter 1b to pass in front of the star, how long it took the planet to complete a full orbit around the star, and the magnitude of how much the brightness dimmed when the planet passed in front of it. Next slide. Before I talk about the data we collected and how, I have to mention that what we had to assume before we collected and analyzed any data. In order to do the experiment, we needed to assume that the planet was circular, that the mass of the planet was bigger than the mass of the star, that the planet itself was dark, that the surrounding light came from the host star, the eclipse had a flat bottom, and that we know the orbital period of the planet. Without these assumptions, the experiment was a lot more difficult or even impossible. Next slide. Now on to the steps we took to get our final data. First, we took back-to-back 200-second exposures. We started taking photos at 10:43 p.m. and our instructor, Ken, got up to stop the telescope at 3:14 a.m. We ended up getting 77 total images, 5 of which were cloudy, which was actually pretty lucky. Normally, there would be more photos with clouds in them, but most of our photos were really clear. Can you click? Once we had our photos, we located the host star, which is the V in this photo, and 8 comparison stars, which are the C's in this photo. Click again. The final steps were to do some calculations and plot data to calculate orbital parameters. Next slide. Ken developed an algorithm to help us calculate the orbital parameters because without his help, it would have taken us a significantly longer amount of time to find our answers. But in the end, we calculated that the duration of the transit was approximately 0.07 days plus or minus 0.0016 days, that the magnitude of the dip in brightness was approximately 0.026 days plus or minus 0.001 days, and that the orbital period was 0.023 astronomical units. We used several equations that Ken showed us and both calculated some things on our own and some things with him. Click again. We finally used a previous study of Cutter 1b done in 2018 by Ken to find the best fit line using our combined data. Fitting the data resulted in a final orbital period of approximately 1.42 astronomical units. Click. Google says the orbital period of Cutter 1b is approximately 1.42 astronomical units, so I'd say we did a pretty good job. But something that could have improved our research and helped eliminate random error would have been to do the multiple tests. Next slide. In conclusion, the radius of Cutter 1b is 1.275 times Jupiter's radius, and the distance Cutter 1b is from Earth is 0.977 astronomical units. I did a little more calculations and I found that the solar flux, which is the amount of light being radiated on a given area, on Cutter 1b relative to the flux on Earth is 1,018.35311 watts per meter squared. This means that the radiation of the host star on Cutter 1b is approximately 1,000 times greater than the radiation of the sun on Earth. Next slide.
Okay, hi everyone, and today I'm going to be talking to you about our third project, which is looking at M92, and I apologize, there's lots of animation, so I'm going to be saying click a lot, click please. And our goal here was to show stellar evolution in a globular cluster using a color magnitude diagram. Next slide, please. and then click again. So what is a globular cluster? This is definitely something that you're going to need to know based on our project. Click again, please. So globular clusters are large clusters of very old stars that are tightly bound together by gravitation. The clusters are largely spherical and orbit in the halo of their galaxy. Stars in a globular cluster have largely the same chemical composition and were formed at about the same time. Globular clusters are much older than open clusters, which is the kind of cluster that Mateo talked about earlier. Next slide, please. So if you're wondering what a globular cluster looks like, this is actually a picture we took of M92. So if this helps you better understand, that's great. Next slide, please. So our procedure, click please. Our first step was to take photos. Click again, please. We took 7 200-second exposures with B and V filters. So the B filters were blue light and then the V filters were green light. Click twice, please. Our next step was to process the photos. So we had to calibrate, stack the images so that if there's any stars in the background that were meddling with the data, or if there's any dust on the camera, this is when we got rid of that. Click twice, please. The next step was to use AIP for Win and specifically the magnitude extraction tool so that we could get the data out of the pictures we took. We collected the coordinates, their brightness, and the B and V filters. Click again twice, please. Thank you. And then finally, we had to calibrate the data, which is using comparison stars to basically check for your accuracy. And I'll go more into that later. Click, please. And then click again twice. So we ended up gathering data from 1,636 stars, which is pretty incredible. Click again, please. And as you can see, this is clearly not 1,636 stars, but it's just an example of what one of our data tables looked like in the initial gathering of the data. Next slide, please. Okay, so the first thing we did once we had our data was to calibrate it. So in order to calibrate it, we chose 5 comparison stars. And like Mateo said, we already had the B and V values of those. We knew what they were. Next slide, please. And then click twice. So once we knew what we thought the B and V values were, our found ones, that's the little b and the little v there, we found the difference between them. So as you can see, our B values were consistently over the actual V values, and our V values were consistently under. So after we calculated the difference between them, we averaged it. And then click twice, please. So we had our average differences, and then we corrected the data by adding or subtracting. Again, because our V values were a little bit bigger, we added, our V values were a little bit less, so we added to get it to that point, and then our B values were a little bit more, so we subtracted. Essentially, this step is just trying to get the data as accurate as possible. And then click twice, please. Then we had to deal with the extinction coefficient, which is essentially just how much the light is scattering to get from the cluster to the observer on Earth. And because globular clusters are in the halo of their galaxies, like I said earlier, the extinction coefficient isn't super big. So click again, please. So when we combined and found B minus V in order to get this column over here, we just subtracted the extinction coefficient of 0.02. And then we got our final B minus V values. And so what are we going to do with this? Well, the first step, click twice, please, is to make a color magnitude diagram like Mateo and Savannah were talking about earlier. This has the B minus V values we found on the x-axis and the magnitude on the y-axis. And then click twice, please. And then we have to fit the main sequence because we're trying to see what the evolution of the stars in this cluster are. Because stars actually evolve as they get older. Most of the time, about 90% of their life stars spent on the main sequence, but we just want to see where this M92 cluster fit in. So then next slide, please. And then click. So this is what our diagram ended up looking like. Each one of these blue dots is one of the stars, and that red line is the main sequence. So as you can see, most of the stars in M92 have evolved off the main sequence. So that's super interesting. There are still more along this main sequence, but they're too dim for our telescope to pick up on. And click again, please. So this is another example of what a color magnitude diagram looks like. And as you can see, we kind of have that top half of it. So if you could click again, this little red circle is more, if you're wondering what I was talking about, this is where it looks like. We have the asymptotic giant branch with that little part on our diagram, and then we have more of the red giant branch. So based on gathering our data and making this graph, we can figure out that most of the stars, or a good chunk of them in this cluster, are part of the red giant branch. And in order for a star, what happens when a star gets off the main sequence and goes to the red giant branch, is the star's temperature cools down, it brightens, and then the radius of the star increases. And next slide, please. And then after we finished our first 3 projects, I think we had like a day or 2 left. And so our mentor Ken was like, hey, do you want to take a pretty picture? And we were like, yes, that sounds fun. So if you could click again. And so our goal here was just take a beautiful picture of the night sky. And then this is what we ended up taking. This is the Veil Nebula. And it was really fun to sort of wrap up our project and have a good time with the group and Ken. Next slide, please. So thank you so much for listening. That's a wrap on our presentation. Thanks to all the group members and for Ken, our amazing mentor, for doing this. We had a really great time and we're super excited to share this with you. So thank you all so much for listening.